the details, right, in the entire chapter, you are sorely mistaken. There is no such thing as a crash course that can go through everything, right, in detail, right? If you miss the detail, you will miss the marks. So how? You're in a contradiction. So what you can do is this: when you're watching my lesson here, right? This is my the lesson that I just sent out. I mean, I sent this out in the group chat down here, right? You see all this part 1, part 2, part 3. Okay, so if you watch the lesson and you decide that, oh no, what, I want to speed run, I turn on the subtitles. Okay, then I turn on the playback speed. I turn it to how fast you want? 2. Bam. Okay, right. So then you can see me at twice the speed. Okay, right. Then you don't have to wait for me to you don't basically sometimes I pause because I have to see them think, right? I have to see you all think, right? Right. Then you don't have to pause and you don't have to wait for me to see your thinking down there in the background. Okay, right. This is a crash course if you want, but basically you'll cover all the points. If I tell you that, oh, you know what, I'll create a crash course for you where I omit some details so that it feels like a comfortable crash course for you because you want a crash course, right? So some people are just dying for crash courses, right? And then I said, in order to get a crash course, I'll omit some details. Means that I'm intentionally removing some points from the lesson just so that I can fit it into a crash course to make it palatable for you, right? Please understand that that's a really dumb thing to want, and that's a really dumb thing to do for me, because then you miss the points, right? You miss the points and then you will lose the marks in the exam, okay? But of course, you might be thinking like, oh, but then that will make me feel good. Feeling good doesn't get you your A's. Okay?
Is the crash course for you here?
Yes. Whoa! They expect it, right?
I don't having normal lesson.
Then what I send the videos for? Do you not see my message? Do you not read the message? No, 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 no. You see, I see gray ticks. Means some joker out there hasn't read it yet. Maybe, but I really don't care. Right? I already sent out already. Right? I sent it out. Guys, this is what? This is 3 lessons worth.
Yes.
3 lessons worth. This is 3 weeks of your time condensed into term 3 week 1, right? This is 3 lessons worth. You want to pay for it? Can I can charge your parents for this, right? I just said that, hey, since I sent it out, I charge you for it, how about that? You know what's the problem? The problem is you all don't know how to appreciate free stuff, right? When I give it to you all free, right? Free no value one right? Free must be fake, right? Free, okay, can? Right, this is what happens when I give you free. Okay, right? This is what happens when you don't put a value to it. So you know what? Maybe I should charge you all. This one, each of the videos here, I charge you $90 for it. 90. Okay, $270. I'll message your parents. Since I send this one out, right? I'll be charging you for 270. Okay, how about that? Then you will suddenly realize, oh shit, right? This is expensive. Let me go and watch it. Okay. This human nature, right? Unfortunately for a lot of students, this is what I have to. This is the tone that I have to pick up on, because otherwise you won't wake up. Right? It's already freaking July. Right? You haven't woken up yet. Of course. If it's not stressful, then what's my value? Anyway, we want nice and happy, is it? Okay lah, guys. It's okay. You try harder, okay? Work hard, okay? Gambate, okay? Alright, so there you go. So I sent it out before and I sent it out again. It's right here. You don't want me to go through this from scratch again because you're going to spend another 3 weeks, right? I'd rather go back to revision. So let me go through the syllabus very quickly, right? What does the syllabus want you to do? The syllabus wants you to, right, do this. Rutherford alpha particle scattering experiment. What was that? That was a gold foil experiment, right? So we fire the alpha particles at the gold foil, right? What were the outcomes of this? What do we learn from this? What do we understand from this thing here? What do we learn this from here?
Energy mass conservation.
What are you talking about? No, small size of the atomic nucleus. What do we learn from this? What are the 3 things? What are the 3 observations? You told me that I went through this, right? I went through the first part, right? Yeah, I went through the first part. This is in the first part. Yeah. So what are the 3 observations and 3 deductions from this experiment? 3 observations, 3 deductions.
Like the thing is so small that there's like
Most Past observations first. Most pass through undeflected. Undeflected. Okay? Right. Then what's the next one?
Slightly deflected.
Some slightly deflected.
Then very
Slightly deflected.
Then few is large angle deflection.
Few, not zero, is largely right. Large angle deflection. Not largely, large angle deflection. Large angle deflection. Okay? Alright. So what are the deductions for these three? What's the deduction for these three? Size of the nucleus is very small. The nucleus is positively charged. The nucleus is very dense, very massive. Right, what else? There's a lot of space between nucleus. If you say there's a lot of space between atoms, you're going to get it wrong. Right? They're going to mark you down. You won't even know. Okay? So there's a lot of space between the nucleus. Do you realize that in the A levels, if you write down an answer and you think it's correct, and then you go and do it and you feel very confident, you come back, you got a C, right? Why? Because you thought your answer was correct, right? And would you ever know? You will never know. In fact, you will never know ever again, because you'll go to university and you won't even know whether your answer was correct. You won't even remember. Okay, that's the worst thing. That means you're walking away with a set mistake in your head that you will never be able to come across, fix, in the future, right? That's the problem with the A levels. That's what I don't like about the A levels, because you will never know. You will never know your mistakes. You can never learn from your mistakes. The next one is, right? The next one will be nuclear number and proton number. What's this? Give me the symbol. Right? You got your A to Z and your element is X. Okay, what's A? What's A? This is your nuclear number Z. Proton number or your atomic number, right? So AZ, right? And then X. Okay. Then you can understand isotopes. Okay. Oh, what's isotopes doing here? Isotopes shouldn't be here. Isotopes should be connected to here. Yeah. Isotopes should be connected to here. Okay. But anyway, it doesn't matter. Okay. Nuclear reactions. Do you understand nuclear reactions? Right. That means it's reactions about the nucleus. Right. That's why it's called nuclear reactions. So your protons and your neutrons, right, may be interchanged. So when you interchange your protons, you get a completely different element. Look at that, right? Nitrogen is 7 protons, oxygen is 8 protons. Okay. Then you have nuclear number, charge, and mass energy, right? Has to be conserved, right? All your mass number must be conserved. The charge must be conserved in nuclear processes, right? We can go through that later, but this is a generic thing, right? Syllabus point E is to apply to everything, right, in your syllabus here, right, in the chapter here. Okay. Then we have this idea of mass defect. I'll go through some mass defects later. Okay. And then we have E equals MC squared. Then we got binding energy. Then binding energy per nucleon. Look at that. What's the difference? Binding energy versus binding energy per nucleon. Okay. And then we talk about fusion fission. Now, if you want to break nuclear into 2 parts, right, for you to learn, right, for you to revise, then you should draw the line here. Right? You can understand, right? Fusion, fission, right? 2 parts. So this is, okay, the first part here. Okay, the first part here, this is the general nuclear stuff. Then you can, break it off here like this. Like this. This is fusion, fission. Fusion and fission. Okay, and then we can, then this whole chunk here is decay. Do you see that? Do you see the in proportion, right, of the syllabus, right? Fusion, fission is here, and decay is here, like that. That's decay. I'm doing this because I want you to remember that fusion, fission is not the same thing as decay. It's not even like decay. Right? So I have had some students over the years, right? They always tell me like, oh, this is too complex to understand. Can I think of it as fission is something like decay? Sure, go and get your C. right? You think of it that way, go and get your C, right? I don't care, right? If you wanna get an A, right? You're gonna want to get a B. Please remember that fission is not the same thing as decay, right? Some people think they try to simplify ideas. Appreciate the complexity, right? So there you go, right? So that's the thing. So your general idea here, everything, this is general. This applies to both this and this. But when we start talking about fusion, fission is this, and we start talking about decay is everything here. Okay, which is separate. So for the first part of my notes, right? If you have my notes, do you have my notes? Hang on, Yeah, my notes are online, right? I saw it just now, right? I cited it just now, right? Yeah. Hang on. So for the first part of my notes, I went through model of the atom. This is your Rutherford alpha particle scattering experiment, right? You fire alpha particles at the gold foil, right? You will get your the observations, the 3 observations and 3 deductions, right? It's all there, right? It's all there. Okay, it's all there. Then you have, according to the notes, AZX, right? What I mentioned about just now. But we have this thing called atomic mass unit. So this is not in the syllabus, but you need to know this, right? So did I go through this before? I've gone through this before, right? And I think in one of the previous lessons. But for those who are like kind of like new to this, haven't watched the videos yet, please understand that today's lesson is not teaching you everything from scratch. I've provided the 3 lessons already. It's all there. If you tell me that I prefer you prefer me to teach it from scratch and you don't want to watch a video, I'm sorry. I know you don't like watching videos. But what's the amazing thing that I understand about you is that even though you don't like it, you still do it. Right? Even though you don't like it, you still do it. Just like how I feel about physics. It's a stupid subject. It's a dumb subject. Do you need to know this in life? Don't need, right? I like teaching it. I like teaching you all to understand a dumb subject. Right? It's super annoying. And the way that they teach it in school also is horrible. That's why I like teaching it. So anyway, so my point is, right, even if you tell me that you don't like to watch the video, then I'm really sorry, but that would just mean that you want me to cover it over 3 lessons. But if you want, you say like, oh, Sam, can you just cover it in 1 lesson? Can. That's what I'm doing now. So like some people are just contradictory in their way of thinking. It's hilarious, man. Anyway, so only carbon has this kind of symbol like this, right? So when you want to represent the mass of carbon, right? Mass of carbon 12. So mass, so write this down on the side. Hang on, sorry. Okay, mass of carbon right here like this. Right, so mass of C12, right? Only the mass of C12 is written as 12.000000 U. Okay, so case in point, I want you to remember that every time you express any mass in terms of atomic mass unit U, you have to put in at least 5 to 6 decimal points, right? I've seen many students that when they get the answer like this, let's say, so for example, they got another, like, mass of another, right, element, and then they write 238.10724, for example, right? Then they round it off 238U, like that. Okay, all right. The next thing they know is they lose the mark, right? In their tests and exams, school test, school exam, at least you know that you made a mistake. However, in an actual A-level exam, you won't know that you got it wrong because you thought they were doing the correct thing. You thought that, hey, I should round it off, and you round it off and you lose the mark. Okay, and then you don't even know. You don't even have a chance of wondering why you got it wrong. You only have a chance of wondering why you got a C. Right? That's the danger of the A levels. Okay, you never know what you're gonna get wrong. So you make sure you get everything, all the details right. If not, why I go through all the details, right? So you got to write it as the one with the many decimals, right? 238.10724 U, right? You must leave it as U. Okay. Then what do we mention about this scenario here? What were you trying to do? As in, what were we trying to do here in this nuclear reaction here? We're trying to make a nitrogen nucleus, not atom, right? Not atom. Okay, what does it take to make an atom, guys? What does it take? If let's say you think that, oh, this is an atom, What does it take to make an atom? What do you need to add? You need to add electrons. So here's the thing, right? This chapter is called nuclear physics. Nuclear physics because we're learning things about the nucleus, right? So this is the nucleus, right? And it's made out of 7 protons, 7 neutrons. And in order to make this nucleus, you need 7 protons. If you say that this is an atom, then I have to add in 7 electrons. Does that make the mass defect difference? Right? A little bit. A little bit. Yes, it makes a difference. Yeah, it makes a difference. But here's the thing. Okay? At bigger elements, that difference will become very significant. Right? I just did a lesson with ACSI, the IB side, right? And what happened was they had a test. This was last year, right? They had a test, right? The teacher go and use the atomic binding and they go and use the atomic mass. He went to use the atomic mass, right? He put it in. When the atoms are small, it is so slight you can't detect it. But he went to use a big atom, 90 protons, which means 90 electrons. When it came to 90 electrons, the mass defect became significant for the electron. So in all cases, please remember that we are only dealing with the nucleus, so omit all electrons if you can, right? So only protons and neutrons. Okay, now if it doesn't make sense, right, to you, try your best to make sense of it now. The understanding is when you make a nucleus, when you squish all the protons and neutrons together, right? So I always like to show like a visual like this. Okay, right, a visual like this. So you have all your protons and neutrons like that, right? Your protons and neutrons, and you're trying to pack them all into the nucleus. And if they don't fit, what you need to do is you need to just kind of like shave off some mass. But you're just, you know, a proton that has some mass that's been shaven off is still a proton. And then when you try to pack it all into a very tight nucleus space, right, there's going to be a mass defect. And this happens for all the elements. All elements, right, will have a mass defect when you create it from the protons and neutrons and you squish it all in and you make a nucleus out of it. Okay, right. Case in point, please look at this. This tells you that the mass of a proton is slightly higher than 1U. This is the mass of the neutron, which is also slightly higher than 1U. The understanding is 1U is like the average nucleon mass in the nucleus. Okay? This 1U, this one here, I didn't mention this in the other lessons. I didn't mention it in the recording as well. Right? Because this is the layman's understanding. The problem with layman's understanding is sometimes I tell you, right, then you know what you do? You go and write that layman's understanding in the exam. Okay? Then when you do that, you get it wrong and then you say, Che, how come I got it wrong? I thought you said that because you forgot that I said that this is your understanding. The layman's understanding. Okay? Layman's understanding is that 1U is the average mass of a nucleon in a nucleus. Okay, that means if you take the nucleus and you just cut it, let's say this one has 14 nucleons, right? And you cut it, each of them is approximately 1U, which also means that your proton, your individual proton and your individual neutron is actually higher mass when they were out there on their own. So individual protons and neutrons will always have a slightly higher mass than the actual protons and neutrons inside a nucleus that's been squished together into a tight space. Because you kind of like, the analogy is you kind of have to shave off some mass. The difference in the mass is called the mass defect. Right, the difference in the mass, so you find the total mass here. Right, the difference in the mass is called the mass defect. Right, this is your del M, this is your mass defect. Okay, then of course the question is what happens to this mass defect? What happens to the difference in mass? What does it become? It becomes energy. So when you have a mass defect, you automatically get energy released. Right, immediately you get a release of energy. Okay, this? Yeah? Okay, good. So the idea of calculating this mass defect into energy, what's the equation? E equals to del mc squared. Okay, right? E equals to del mc squared. So the mass defect that you get, right, is converted to energy. E equals to del mc squared. Understand this? Okay, question time. Do we do this on a normal basis. Like for example, you walk into the science lab one day, right? Even those professional science labs, you walk in there one day, right? And you look at the researcher. Is he sitting there trying to create nitrogen 14 atoms from constituent protons and neutrons? Kind of like he sit there and then he do this. Or maybe you think this is a natural process. This happens in nature. There are protons and neutrons flying around and then they combine and then you become nitrogen 14. Does this happen? Absolutely not. This is in theory only. Nobody does this on a normal basis. This is just us trying to understand the theory of it, right? Nobody is going to sit there and create nitrogen 14. This is for us to understand how the mass defect becomes energy, right? Okay, so don't go and think. I mean, I had one, right? Okay, right. I think maybe because the person didn't take chemistry, but then the idea was that, oh, this happens in the air. There are protons and neutrons flying around, and then that's how we get nitrogen in the air. Okay, unfortunately, you also realize, right? The person also forgot that the nitrogen in the air is not just N, it's N2. Right? This is just atomic N. So this is in theory only. Nobody is gonna go sit there and then make nitrogen like this. Right? Maybe it happened, at the start of creation. Maybe there's the dude out there, he's like, let me make some nitrogen. Maybe, I don't know. Maybe he had all the time in the world. Get it? Or maybe I think for on that scale it would be he had all the time in the universe. I'm talking about God. Yeah, God don't need nitrogen.
Sure.
Okay, anyway. So you get what I'm saying, right? So the idea here is that nobody does this. We use this to calculate the energy. And this energy is known as binding energy. This is known as your binding energy. This is called your binding energy. Okay? Right. So if you want to use E equals to del mc squared, what's the rule again? Del m must be what? In kg. So this is a physics equation. All physics equations uses SI units. Del m must be in kg. So you go and find the mass defect. So if they give you values in U, right? You use the U to find the values, right? The mass defect in U, you need to convert it to kg, then you times C squared. Okay? And then you have basically this next page here, right? And in the next page, we're talking about like how E equals mc squared, right? How we derive the equation for energy. Get this? Okay, we had a shortcut, right? We had a shortcut, right? Is this the value that we used? No, right? What's the value for the A level 933.75? Okay, so it's about 933.75 MeV. This is the A levels version because the numbers are a little bit different, right? From your formula sheet, right? These notes I recycled it from my IB site, right? So they use 931.5, you guys use 933.75. How come it's different? I don't know, man. Right? I mean I know there are two different numbers, so I'm just gonna tell you that I'm aware, right? So if you have like IB friends or if your IB friends have JC friends, okay, and then they are comparing notes and all that, you realize that these two numbers are different. Okay, so this is a shortcut. Okay, so when you convert the mass defect into energy, you can use this shortcut 933.75, right? You can use this shortcut, but can you do that in an exam? You cannot do this in an exam. This number 933.75 is not a number that you memorize. It's not provided for as well, right? You would have to do this thing, everything here from scratch. I don't make the rules. This is how it is done for 40 years already, right? Right? Since before my time even. We have to always convert it to kg, E equals mc squared, get it in joules, and then convert it back to MeV, right? That's the problem, right? So this conversion is a shortcut, right? Every one U of mass defect, it will give you 933.75 MeV of energy release, right? Then the next thing is I want you to memorize binding energy. Did I get you to memorize binding energy the last time round? Binding energy, did I ask you to memorize binding energy? What's that? Huh, what? What's that? Energy? So the energy release when you bind the constituent nucleons, right? To make what? To make the nucleus, right? To make the nucleus. Or it can be quoted as the energy required to break the nucleus into its constituent nucleons. So backtrack a bit, go back to this equation here, right? Go back to this equation. So this equation tells us that if you want to do it the other way around, you can. Okay? You want to do it the other way around, you can. That means energy, you add it to 14,7 nitrogen, you can get 7 protons and 7 neutrons. Okay? Right? If you do it this way, you can do it. Again, do we do this on a normal basis? No, nobody's going to do this. Like who does this on a normal basis? No sane person will go and do this for fun. So if you want protons only, you go and ionize hydrogen. Right? If you want neutrons, that's interesting. There's another radioactive process that produces neutrons. Right? There are some radioactive materials that can produce neutrons, but that is completely not in your syllabus. Okay? Right? So for you, you only need to, I mean, that's an interesting question. But if you want individual protons and neutrons, you can, but we are not doing this on a normal basis. Hey, hang on. What do you understand? No. What do you understand? So, if you use energy to break the nucleus into individual protons and neutrons, right? What happens to the total mass? The total mass increases, so there's total mass gain. Okay? And this is the part where some students get really confused. Huh? You mean the mass will increase? But why? But why? Okay? So you keep asking why, it will never end. So you just have to quickly accept that mass defect releases energy, you supply energy, you get mass gain. Okay? Don't need to ask why. It's just like that. Which is why in physics we have this concept called the conservation of mass energy. Okay? The conservation of mass energy. I didn't make up the word myself. It's in your syllabus as provided by SEAB. Right? Ministry of Education, Singapore. Who's the minister now? Desmond Lee is the Minister of Education. Yeah, okay. He signed off. He's the one who said, okay, I want all my A-level students to know this term, mass energy. Right? Because if he didn't sign off, who approves of this? Must be him, what? Or maybe the previous guy, lah. Then he take over, he wouldn't realize, right? Shit. Okay, anyway. So then the next thing is, finding BE is not good enough. What do we do with the BE value? So even if you find out like, oh, that's the energy release when you create the nucleus, right? What do we do with the BE value? Like the BE value that we obtained for nitrogen 14. Anyway, what was the value here that we got? 101.25 MeV. Okay, so this was the amount of energy that we got from the previous example, right? All the mass defect, you calculate all the mass defect, then you get this value here. And then what do we need to do to this value? This value tells us, okay, if you want to break a new nitrogen 14 back to its 7 protons, 7 neutrons, you have to have at least minimum amount of this amount of energy. So what happens? What do we do with this value next? We divide it by the mass number. Yeah. So we find BE per A. Okay? We find BE per A. We take the BE divided by the A. Alright, so we find this. So the BE per A of N14 is equals to 101.25 divided by 14. Not some random 14.00 something, whatever. It's just 14 because this is the mass number. It's not the exact mass. So it's 101.25 divided by 14. And what's the value that we got there? Eh, you didn't calculate this, man? Okay, calculate this now. Say what? 7.23 MeV per A. Okay, in English, what this means is that for nitrogen 14, let's say you have a nucleus of nitrogen 14, 7 protons, 7 neutrons all squished together in one tight container. On the average, you will require 7.23 MeV of energy to pull every one nucleon out. You pull one nucleon out, you pull another nucleon out, right? It will require 7.23 MeV of energy for each nucleon. You understand that? Okay? All right. So then we come to this point where we have this graph. So this graph was what? What's this graph all about? Come, tell me what's this graph all about. So on this side, it says the average binding energy per nucleon. Look at the y-axis, right? It's written there. I think I don't have to teach you how to read, but there you go, right? Average binding energy per nucleon. And this here is your nucleon number, okay? So it turns out that nitrogen 14 is around there, 7 point something, right? So it's on this list here, right? This is the entire list of all the elements, right? All the elements in the, I mean, just a summary of all the elements in the periodic table, starting from hydrogen 1, which is one nucleon number but 0 Be per nucleon, and then you, right, because hydrogen 1, what's hydrogen 1? Yeah, just a standalone proton. Okay, just a standalone proton. Is there any binding energy to it? Why not? Because the standalone proton is not bound to anything, right? So it's by itself. So the binding energy of one single proton is 0. One single neutron will also be 0, right? Then we start draw all the way up to this point here. We end off with uranium-238. Okay. In the actual lesson itself, I asked you all to draw this graph here, right? To sketch a graph here, which is a summary of that graph there. Right? Please refer to the video to watch to learn how to draw this graph. I'm not going to go through it. Why would I go through it again? Right? Yeah. Okay, but what's the importance of this graph? What does this graph tell us? Iron 56, which is at the peak of this graph, right, will require the most energy to no. Okay, iron 56 will require the most energy to pull its nucleons out one by one, right? Like how much is it? How much is it? Approximately, if you look at the graph, how much is it? About 8.8. Right? If you look at the graph here, it's about 8.8. This is 8.8 MeV, mega electron volts. 8.8. So every nucleus in iron 56 requires 8.8 mega electron volts to remove. So you remove one, right? Then you have to use 8.8 MeV. Remove another one from iron. Oh, you have to use another 8.8 MeV. Remove another one. Okay? So altogether, per nucleon, iron requires the most energy out of all the elements to remove every nucleon from the nucleus. Okay? So what does that mean? Yeah, iron nucleus is one of the most stable nuclei in the universe. Okay? And therefore, we understand this graph is for us to determine what? So usually on your school's notes, you will see a line drawn in the middle, right? To the left, you didn't label this, man? Or you labeled it on the other one? Okay, can, right? So to the left of it, what do we understand? Okay. So on the left-hand side, you will see your school's note, right? What? Fusion, right? And then on the right-hand side, you will see the school's notes, right? Fission, right? Okay. It's not about more likely. It's not about more likely. The context is this. If these elements on the left-hand side, they do fusion, what will happen? Energy will be released. That's a key point, right? That's the key point. Energy is released. Energy is released, okay, when you do fusion of the elements on this side. Okay, in a way, you can think of it this way. Let's say you fuse small elements here. The small elements are all here. They have very low Be, which also means that they are pretty easy to break apart, which means that they are unstable. And if you make them go through fusion, what happens? They become bigger, right? As you become bigger, as you go towards the right side, you will go up the graph. As you go up the graph, you basically create elements or nuclei that are more stable because they have higher Be per A, harder to break. So if you go from unstable to stable, right, you would release energy. So that's another indicator. Okay? Okay, listen up. Am I saying that these elements cannot do fission? Can they do fission? Can. But if you want these elements to do fission, what must you do? You need to supply energy, which is something that you should not do. right? I don't want to supply energy in nuclear reactions. I want to think American. I want to extract energy from it. I want to pull energy out from it. Okay, I want to get the energy out. So I don't want to supply energy to you. I want to take the energy out. Okay, so fusion of the elements on the left hand side will release energy. Fission of elements on the right hand side will release energy. So you want to write down, right? Energy is released this way. Okay. One more time, please do not. Don't even bother to misquote me. Right? I did not say that elements here cannot do fusion. They can, but if you do that, then you'll be going this way, and you need to supply energy this way. Right? So that's why the two arrows point like this. Right? If you don't understand why your school's notes are pointing this way, and this way, now you know. Okay? Like I said again, this one I'm not going to draw it. Go and watch the video if you want. Right? I'm going to leave that to you. So two of the more popular fusion fission equations that we have is this, right? Fusion of deuterium. This is a very simplified version of it, right? I took this from the textbook as an example. Okay, so when you fuse these two, where are the deuteriums on the graph? Where are they? Where are the deuteriums on the graph here? Right? Yeah, the two H's, the two H, right? Deuteriums, which is here, right? And then when you fuse them, what's the product? What do you get? You get helium, right? Helium-3, which is slightly above. Okay, you see helium-3 is up here like this. Okay, so when you fuse two deuteriums, you get a product that is higher up on the graph, right? So in a way, you can tell that energy will be released. Okay, so it makes sense, right? So fusion, right? Fusion of small elements getting a big element, right? Big nucleus, you will get a release of energy. So energy will be released this way. You get what I'm saying? Yeah. So I'm gonna ask you this very quickly. What do you think about the mass? How about the mass? How about the mass of this compared to the mass of that? Is there mass defect? Is there mass defect? Huh? There is. How you know? How you know there's mass defect? Because energy is released. If you know that energy is released, means that there is mass defect. That means you lose a bit of mass from your nucleons. Okay? Alright. Same thing here. Fission. I'm going to fission uranium-235. This is also another one of the more popular fission reactions that we use as an example. Right? Of course, this is not the only one. Right? This is the fission. Did anyone say something? Okay, I guess not. Alright, so this is fission. You take uranium-235, you go and fissure it, you break it into smaller elements. Barium, krypton. Look at it. Where's uranium-235 in the graph? Where is it? All the way here. Right? Where is the barium and the krypton? Right? Barium, krypton. Where is it? 144, 89. Where are they? Right? So this is, hang on, sorry. This is where uranium-235 is. Right? 144, 89. 144, 89. 144 is somewhere around here. 89 is somewhere around there. So you break the uranium-235 into products that goes this way. Okay? So just based on the graph alone, do you have energy released? Is this legit? This is legit, huh? Right, so I'm gonna ask you this. How about the mass? How about the mass? Let's compare this mass and compare all these masses here. How about the mass? Is there mass defect? There is mass defect. Alright, there's mass defect. At this point, in my past experiences, in the past lessons I've conducted, I've got students that somehow sitting there not paying attention, realizing that, mass defect? How come the numbers still add up? 1 plus 235, isn't that equal to 144 plus 89 plus 3 times 1? Like, but the number is conserved. How come there's mass defect? So how do you slap them into existence? No. That's mass number. That's not the mass defect. That's mass number. Mass number is conserved. The actual mass itself is not. Right? Yeah. You know, that's a problem, right? Like after all that, right, the students sit down there, but I thought the mass number is still the same. Obviously not paying attention at all. Right? How do you get them to pay attention? You tell me. How do you get this kind to pay attention? Huh? Just heck care, right? I mean, what else can I do, right? I'm already shoving this concept down your throat already. Then what else do you want me to do? Right? Maybe it's the tone. I've heard this before. Your tone is very scary. Okay lah, guys. Then I shall go with a softer approach, okay? All right? Everybody 加油, okay? Okay? please remember that for the love of your grades, not to get a bloody C, right? Make sure that your 1 plus 2, 3, 5, this one is just mass number, but the actual mass has decreased, right? Give you a passive aggressive tone. How about that? Huh? I love it, man. I mean, in on the big picture, right? I mean, to be honest, I'm just amused by this kind. Yeah, I'm just amused by this kind, right? I mean, of course, it's frustrating at times because already telling you how many bloody times already, still don't want to get it in the head, is it? Already given you the video already replayed so many times, you still don't want to get it, is it? It's your choice already. It becomes a choice, right? Isn't it? It becomes a choice, right? Remember, I said right. Water to the horse. Horse don't want to drink. So what is it? Horse choose not to drink. Okay, look at this. So what we're gonna do now is this, right? The idea here is that you're technically not supposed to know that energy is released. Yeah, you're supposed to go and check. Okay, right? You're supposed to go and check. So you know what? Do it lah. Check lah. Since we haven't done it, have we done this already? We done this already. Okay. So tell me the numbers. Come. What's the total mass on this side?
That is 4.02820.
4.0 4 4.02
820.
one more time. 4.02
8204. What's that saying?
4.028204 and how about the total mass on this side?
4.0.
4.02 4694. Is that right? Okay, so what do you notice about the mass? What do you notice about the mass? Oh, hey, don't scare me. Anthea, not at this moment, don't scare me, don't scare me. Okay, parallax arrow. The arrow pointing this way, okay? Okay, so the mass decrease, there's a mass defect. Okay, so mass defect, right? There's a mass defect, and therefore, right, we can calculate the energy that's been released, right? Okay, so there's a mass defect. So we know energy is on this side, like it could be on the other side, right? But now we know there's mass defect, right? So mass defect will give you energy released, right? How much? How much do we calculate the energy to be? 3.2794 MeV, right? Okay, good. And then, kind of like the answer here is like I've got a couple of landmines inside my notes, right? I told you before that, sometimes it's a bit like off, right? Because sometimes I change the values and I forget to change the answer. All right, there we go. One thing that I just realized maybe like 2 to 3 years ago, it was quite surprising to me. I was like, the formula sheet doesn't give you the mass of a neutron. Yeah, it doesn't. In the formula sheet, they only give you the mass of proton and electron only. The actual formula sheet, not me. Yeah. Yeah. That was because I'm recycling the notes. Yeah. So that's quite surprising to me. So just make sure that you understand that you may have to go and find the neutron mass from somewhere else, huh? No lah, they give you enough information to help you find one. They're gonna ask you to memorize it. Please, this is not chemistry.
Well, chemistry give a lot of like data stuff. It's actually useful.
Oh, is it? Oh yeah, okay. Yeah. Too bad lah. Singapore physics still wants you to memorize everything. Anyway. Okay. Did we do this also? Same thing, right? You go and find the total mass on this side, you go and find the total mass on the other side, and then you find, oh, there's a mass defect, and then energy is released. Okay, good. All right, there we go. Oh, I don't think we. What? Hey, who's beeping me? Shoot, tomorrow I got early class. I forgot. Tomorrow's youth day, right? Yeah. Oh, okay. Sorry, what was the question? Wait, stop. What? There's what?
4 nucleons, right?
I don't understand what you mean by 4 nucleons.
4 neutrons. Okay, anyways.
Wait. No. There's no four protons and neutrons. I don't see where do you see your four protons and neutrons? I don't see it. What? Sorry?
What's the error mass number? So it's like
What? Which one are you talking about? Are you talking about mass number? Or are you talking about actual masses? Which one are you talking about? Because if you're not specific about this, you're not asking a good question. Yeah. You want to talk about mass numbers? Okay, so there's mass number is 2, mass number is 2, there's mass number is 3, mass number is 1. So mass number is the same. Okay? Right. Wait, hang on. You were asking me about the 4 protons and 4 neutrons, right? Do you see 4 individual protons and neutrons here? I don't see it, no? I don't see it. So you cannot assume that there's 4 individual protons and neutrons. Okay, yeah, okay. What's your question actually?
Can they ask, like, they ask energy per nucleon, then it's just 3.4.
Wait, why would they ask energy per nucleon? No, as in, like, where is that coming from? Where's the energy? So that BE per A, right, is when you start from individual protons and neutrons. We're not starting from individual protons and neutrons here. So BE per A doesn't apply here. BE per A is only when you look at every element and you look at what they're made of, then you go and calculate the BE per A. Yeah, but this is not it. This is a legit fusion reaction. Yeah, this is the thing that happens in the sun. Yeah. Did I ask you to cancel this one also? I didn't ask you to cancel. Okay, now I'm asking you to cancel. Yeah. So it turns out that after doing some deep research, right, this energy is not the Ke of the products. Yeah. Right? The energy comes out as gamma radiation. Right? It comes out as gamma radiation. Are we okay in this? Right? Fusion produces gamma radiation. Oh, sorry, I'm just jumping between the two different files. Hang on, let me just close this thing first. Don't care. Okay, come. This one. What's this? This fission. Right? You know what some students will tell me? I thought this decay. It's not decay. Firstly, it's not even alpha, beta, or gamma or anything like that. Right? And secondly, just because it's breaking into something smaller doesn't mean that it's decay. This is fission. Don't mix this up with decay. Okay? So are we right to say that the mass here and the mass there, right, the total mass on the left-hand side and on the right-hand side will be different? Would there be a mass defect? Yeah, there will be a mass defect. How do you know there will be a mass defect? Because it's energy released. Right, so for this question, what was the correct answer? So it's 181. So I messed up on the answer here. Sorry, I keep having to change this. So it's 181 MeV. So those who are online, please make sure you change your answer key as well. 181 MeV. How about this one? Is
7.4.
this was 7.4, so this one's a bit wrong. So 7.4 times 10 to the power of 13 joules. Right, there you go, 7.4 times 10. So please make sure you correct your notes, right? Sorry about that, because, like, you know, sometimes I change the values, right? I go and make some changes, amendments to the values, but then yet I forget to change the answer key. Right? Yeah, I'm not perfect lah. Right. Okay. There we go. Okay, so did we go through this page? Did we? Did we go through this page? Not yet, but did you watch the video? Never, right? How? Okay. Anyway, doesn't matter. We'll go through it now. So this is fusion. This is fission. But likewise, again, I'm gonna go through it as though you have somewhat watched it.
Okay.
Right? Yeah. Because I ain't got time to go and stretch it out to 3 lessons. And you want me to skip some parts? Skip this lah. Okay, go on to the next one. No lah, you think what? You think I hack job ah? Crash course. This lah, oh my god, I'm not a hack job, Ken. Okay, so these are the different types. This is a different type of calculation. This is not explicitly shown in your syllabus, okay? But the questions from JC papers, I will always see this question come out like this. It's the exact same fusion and fission reaction that we saw just now, but this time around they don't give you the mass. They don't give you the mass. What are the values they give you? They give you the BE per nucleon. Okay? So if you see a question giving you BE per nucleon, okay? If you see a question giving you BE per nucleon, right? You know what you have to do? You have to find the no need, no need, no need, no need, no need, no need. Okay? So you have to find the total BE on the left hand side and right hand side. Okay? I mean, I'm not just tell you this, right? There's no need to go and figure out why does it work like this, right? But I want you to see this, huh? Okay, so right now, right here, right now, since you haven't done this with me before, so I'm gonna ask you to do the calculation. Okay? So calculate the total BE on this side, total BE on the left hand side, and total BE on the right hand side. Total BE on the right hand side. There we go. Right, total BE on the left hand side, total BE on the right hand side. Right. Ready, set, go. Find for me the total BE. So be very careful. They provided you total BE, they provided you BE per nucleon of deuterium. That means every nucleon in deuterium is 1.1123 MeV, which means that for one deuterium, you need to take this value and multiply it by 2.
Yes.
For one deuterium. You got 2 deuteriums, so you have to multiply it by 2 again. Alright, there you go. So what's the total BE value on the left hand side? 4.4492 4.4492 MeV. Okay, now find the total BE on the right hand side. 7.71805.8 MeV. Do you see that? Yeah? Okay, cool. Right. Now, ignoring the BE values that you just calculated for now, right? This is total BE left hand side, this total BE right hand side. Hey, hang on. Neutron?
No, no.
Why no? It's a standalone. Neutron has no binding energy. So, I circle this whole thing. The total B is only 3 times this value. Right? So that's how you got your 7.718058 MeV. Correct? Okay, good. Hey, hang on. Let's ignore the values first, right? Ignore first. So ignore first. I just shade it off first. Like that. Okay. Was there energy released from the previous question? I mean, this is the same fusion from the previous stage. This is not like suddenly, oh, I can change this when I want to, right? The sun can't change according to what I want. Was there energy released for the previous one? There's energy released, right? Okay, so do we all agree that I can safely, guys, do we all agree that I can safely write energy is released in this nuclear fusion? Can or not? Can, Okay, write it there together with me. Commit to it. Energy is released. Because for sure, right? Previously, I already showed you the energy is released, right? But I want you to see how the binding energy value changed. Look at it. Look at how the binding energy value changed. Look at that. It increased. The BE increased. And this is the part where some students will be like, hey, I don't understand this. How come the BE increased and yet energy is also released? If you're fast, then you just say, I'll just take it as it is. And every time I get a BE question, anytime I know that the energy is released, that means the BE increase. Or if the BE increase, I know for sure that energy is released. Because that's the truth. Okay? In fact, from these values here, how do you find out the energy release? If let's say these values and the previous page of values is different, okay? Might be the same, might be slightly different, I don't know. But what can you do is this. You take this number, you minus away that number, that's the energy release. Do it now. 3.2688858 MeV. Slightly different, right? But here's the thing. That's very similar to the previous answer, right? 3.27. Rounding errors, rounding errors. Okay? That's my point. My point is that this energy release, right? When there's an energy release, yeah, previous page only. Just the page before only. Yeah, when I gave you the mass, it's slightly different. It was like 3.279 something, right? This is 3.688. It's about the same value, right? I think it's because of the values I got from the internet and all, right? But the idea is here, okay? Energy is released. Okay, how? How to make sense of this? Oi, like what's going on? How come the binding energy increase? How do I explain to a friend that the BE increased and then energy is also released? What? How?
Because that one has more mass and this one has less mass.
Uh-huh.
So if there's mass and conservation, this one has more energy, so that is the conservation thing, right? So that yes. Yes.
Yeah.
Yes, got it.
Okay. I help you with one thing, okay? Right. I think the best understanding is this. Okay, what's our layman's understanding of binding energy? Like binding energy is what? Binding energy is how do we think of binding energy? Binding energy is what? It's like the how stable, yeah, energy required to remove the nucleus, right? Isn't binding energy like an indication of how stable the nucleus is? Right? Look at this, which one's more stable? Yeah, this one, right? The higher binding energy would mean that it's more stable, right? So am I right to go from unstable to stable means that you release energy?
Yes.
Yeah, it is, right? Right, like my kids. You give them sugar, they become unstable, they need to run around like that, then after they become stable. Right, so this is unstable and this is stable, right? That's because someone gave them sugar, right? So it goes from unstable to stable. It's a release of energy. Okay? Do you know what is the real reason? Do you want to know?
No.
Too bad you will know the real reason now. Okay, yeah? Alright, the real reason is this. Come back to this graph. Okay? This graph, binding energy per nucleon is supposed to be a negative value. In your syllabus, right? In the A-level syllabus, in the high school syllabus, you learn that binding energy, you learn this graph, it looks like it's all positive values, but in reality, it's all negative one. If you go and pick up a university textbook, you will see the graph drawn like this. Right? They'll draw for you like this. Like that. It's the other way around. Damn. Don't damn. Question is this. Why is it negative? Why are the values negative? Very good. Nice. Binding energy, by definition, should have been a negative value because the nucleus is held together by an attractive force. What is that force called? The strong force. So binding energy, technically speaking, because it's not the word strong force is not in your syllabus, technically speaking, is the energy required to break the strong forces. And in almost all the other chapters, do you remember GPE? GPE, gravitational force is attractive, right? When the particles are attracted to each other, the potential energy is negative. When you have a plus charge and a minus charge, electric fields, the electric potential energy is negative because they're attracted to one another. So in the nucleus, the particles are attracted to one another via the strong force. So in order to break this strong force, or rather the amount of energy that it, like the potential energy that it has, is also negative. You need to give it positive energy, then you can break it apart. But if let's say you label the BE, right? If you were to draw the BE, actually these are all negative values, because it shows you how much energy you need to put in so that you can separate the nucleons to infinity.
So technically the positive graph is like breaking energy.
No, the positive graph shows you the energy that was released. You see, binding energy has two ways of defining, right? Binding energy can be the energy that's released or it can be the energy that's required. So that's why I much prefer the way to understand it by the energy required, because this helps you to understand which one is stable, which one is not stable, right? Which is fine, right? Either way is fine, but I still prefer the second way. In the exam, when you're asked to define binding energy, you use this statement, right? Energy required to break down the nucleus into its constituent nucleons, you will get the mark, don't worry. Okay? But if you say something like this, oh, binding energy is the energy required to bind the nucleus, you take a paper, you throw it out the window, same thing. Okay? You might as well don't do the exam. Energy required to bind the nucleus, my gosh. The worst thing is that I say already, right? There's still people go into the prelims and still write the same thing. It's like, that I say for what?
I don't get why it's wrong. Is it because it's the same concept?
I never say it's wrong. What do you mean by why it's wrong?
See?
Binding energy required to bind the nucleus. You don't understand why it's wrong? Can I call you by a different name? Why is it wrong?
This is not why.
Yeah, exactly.
Okay. Okay.
Yeah, it's a definition, right?
Yeah.
Yeah, it definitely has been written like that. That's why it's called definition. Yeah, it's not opinion, right? Opinionation, is it? Oh, I feel that the binding energy can be written like that lah. But I feel lah, right? Science don't care about your feelings. Funny one eh. Hey, so technically, right? It's supposed to be negative. It's supposed to be negative.
Okay, that makes more sense.
Right? So you see, right? You go from negative to become even more negative. Then you release energy lah. You release this amount of energy. Does it make sense now? Yeah, it makes sense now. Okay?
What about like mass energy conservation thing? Does that make sense?
Okay, stop. Okay, look at this thing here. Look at it.
Okay.
Which part gives you the mass? Which information talks about mass? Where does the mass come in?
Yeah.
It's got nothing to do with mass. So this is just purely BE based. Okay, this is just purely BE based, right? But my other thing is this. You got to understand this. So some students get a bit confused about this. So I think I'll summarize this for you. Okay, I'll summarize this for you. Hang on, I'll summarize this for you. Okay, if you release energy, okay, will there be a mass defect?
Yeah.
There will be, right? Will there be an increase in BE?
Yeah.
Right, so BE increase, right? Yeah, then that's all you need to care. Yeah, if you have energy released in a fusion reaction, okay, is there a mass defect? For sure, confirm. Don't even bother asking me what if, right? A lot of you all have a lot of what ifs, you know. So mass defect is definite when there's energy released, right? There's no such thing as releasing energy without losing some mass. Okay, it must be related. Then the next thing is, if you go from unstable to stable, you are literally increasing the BE number. So some students get very confused because like, oh, do I say that the BE increase or do I say it decrease? Because it will make sense to me if I say they decrease, then it release energy, right? So I'm going to tell you this, I don't care. I'm just going to tell you that the numerical value of BE is larger. The numerical value, like the number is bigger, the absolute value is bigger. I don't care whether it's positive or negative, right? I don't care anymore. I'm just telling you, like, how they learn in university, right? So this is an increase in binding energy. Can? Okay, good. Do the next one. Look at the information given to you and do this on your own. Now, while I take a break. Yeah. I'm gonna go and take a toilet break.
get the what's it called? You see, like, for example, materials, they like bigger pattern, they like it's really in the account that next day that translating. Like I thought we need to take in the no. I thought always need to take into account. Because like he said when the item is very big, the value is more significant. But it always have to, yeah, it's always real. He's saying nucleus and atom. So it's like educate. Well, it's not really confidential.
Yes. You had a physics test.
I thought I passed in the before.
Oh, the BA exam lah. I thought you had a test.
Like remember you finish half of it. When it's ridiculous.
Any questions so far?
It's okay, but then like.
No? Then tell me the answers. So what's the BE on the left side? What's the total BE on the left side? 1783. 0.8709 MeV, and how much is the B on this side? 1957. 4686 MeV. Okay, so is energy released?
Yes.
How much?
What's it?
173.27. Okay, I'll just leave it as 173.27 MeV. Okay, all right. Just MeV. You don't have to use the 5 decimal or 6 decimal point. That's for you, right? So MeV you can just. I think you might have to round it off somewhere also, but I'm just showing you that because of the different numbers I chose, right? The number here and the number in the previous page is different, but I guess like it's similar lah in a sense. Okay, this good. So if you are given mass, check for mass defect. If you are given BE, check for BE increase. Then you know that energy is released. If your BE it gets lesser, that means energy was supplied. Okay? Right? I'm pretty sure at some point some of your tutorials already have these questions. And some people are already confused. How come the BE gets lesser or gets more? Like they don't understand. This is me telling you why you should understand it like this. All right, let's try this one here. Do you try this question on your own? Yeah, try it now. I'm gonna tell you. Okay, so by looking at this reaction, okay, the idea here is this. Is this fusion? Is this fusion? Or is it some sort of like kind of like a reverse decay or something? Okay, it's something, right? Okay, if it doesn't fall directly under fusion, nor does it fall under fission, right? And it obviously cannot be decay because decay is not like that. Decay you can't control. Okay, then this is called transmutation. All other nuclear reactions that's not classified properly is called transmutation. Yeah. Okay. What did they give you?
What's the alpha?
Alpha particle is a 4-2 helium. There.
I just use the vector.
What?
I just use the vector.
Yeah lah, correct lah. So the idea here is yes, they give you mass. So if they give you mass, you can use mass to calculate. So do the calculation for the transmutation. What's the total mass on the left hand side? Mm-hmm. Hmm? Can you tell me what's the mass on the left hand side? Wait. Talk to me, talk to me.
Wait. So
Left hand side is
left hand side is 18.0056.
18.005673U. And on this side,
18.00
18.006407U. Okay, tell me what's going on.
Energy is supplied.
Energy is supplied. There's a mass gain. So you are supposed to predict that, oh, I now know that energy is on this side. Okay, tell me how much energy. Wow, really? No, I want the energy. Why you give me in U?
Okay. 0.68537 MeV.
So 0.68537 MeV. Can you tell me how you got that?
I found the mass increase.
So the mass increase, so the mass gain, right?
Yeah.
Mass gain is how much?
0.000734
734U
times 933.75.
So times 933.75 MeV, and therefore you got 0.68537 MeV, correct?
Yes.
Okay, good. Right. So everyone, pay attention. Are you supposed to do this?
No.
You're not supposed to do this, okay? This is unfortunate. A level wants you to calculate from scratch, but we are doing a crash course here. Speed run. Speed run. Ain't nobody got time for that. Alright, so we're just gonna do this. Just remember, right? Not allowed, right? At A levels. Okay, you cannot. Okay, but someone asked me this question before. What if I show the working 1U, right, convert to energy, right, then 1U times 1.661 times 10 to the power minus 27 kg, then times c squared, then convert to joules, and then what if I show the working here and I got 933.75 there, and then I used it to multiply to this? Can. In fact, I would think that's a smart idea. No lah, how many nuclear questions can you get? Huh? At most, I mean, at most two, right? Then if you have to do two times, or if it's part A, part B, you can just use it again. It's okay. Yeah, you can. Okay, can we go on to this one now? Yes, it is. That's my breakfast. Okay, we'll go on to this part, but this point onwards, from this page onwards, is called decay. Okay? Decay? 3-minute break. Yeah, take a break. I mean, I went for my toilet break. You're doing work, right? So now it's the time for you to take a break. 3-minute break, 3 to 5-minute break, right? We're doing decay. Yeah. I took out my mic so I can't hear anything. If anyone online wants to say something. Snacks? No? You want me to give you the nice ones? Oh, I didn't hear.
Okay. Nah.
No? Kit Kat strawberry?
Yeah. Bro, you asked me chilling at home and stuff. You have to push it, yeah. So like, so like, oh wait, yeah, I do. What did you play for us? What's your morning? Six. Like, I would go to like 6 months out. Why? Then he would say that he would say, okay, the diagram, don't how to skip. The report, don't know what to write, skip.
What are you talking about?
Practical.
For what? Physics?
Say skip.
Skip what?
Diagram, the report.
Hey, once I'm done with this, next one is planning. Practical. Yeah. We have to do practical also.
Yeah, yeah, same. Bro, mine is like, you might be dead. Mine is after my actual papers. Yeah, no, wait. Honestly, then we are it's like, we have to replace that. Then we can I got practical. Then some all plan we want
Okay, gonna start in 3, 2, 1. 1. 0.9, 0.8, 0.5, 0.1, 0. Okay. So this page onwards is decay. Okay? Have you all seen this graph in school? You done decay in school already? You done this in school? Decay. But you never see this graph before. Oh. Okay. You don't need to know this graph. Okay? Right. So technically speaking, I agree this graph is really not exactly in syllabus. However, it also means that your school can give you a question with this graph and make you apply to the question. Okay? How can they ask me something that's not in my syllabus? Hey, welcome to Singapore, man. Alright, so what we have here is the neutron and proton number. Again, neutron and proton number. This graph shows you all existing elements. But you know what? Before we do anything, I want you to understand that this graph is not related in any way to this graph. Okay? This is a fusion fission graph. What's the highest one there? What do we understand from this graph? Iron 56 is the most stable and will not do fission and fusion to give you energy. Iron is, it will not, like even if you fission iron, it will not give you energy because the most stable nucleus. You understand this? This graph on in return does not have anything to do with decay. Okay? So when we come to this graph, right? This graph is also about stability, but it's about the stability of isotopes. This graph is about the stability of isotopes. Okay? And this graph tells us, right, the different combinations of protons and neutrons that we have for different isotopes. Okay, Soba? Can I? All right. So it's about how stable the isotope is from decay, which is completely different from fusion fission. Fusion fission is a like a you have to activate it to happen. Decay happens spontaneously. Okay? Fusion fission is one of those processes where it will happen with activation. You need to activate it, then it will happen. But decay is something that happens spontaneously. Okay. So if you look at this graph, what happens is we are listing out all the elements with all their different proton numbers. These are the Z numbers, these are proton numbers, right? Against all the neutron numbers, N. These are all the neutron numbers, right? There's this very thin layer, there's this very thin region, white in color here in the middle, right? That, according to the textbooks, is termed as the valley of stability. Right? Fancy words aside, any element that exists in this white region is a stable element. Right? Any element that exists in this white color region is stable in nature and will not decay. Again, it's got nothing to do with fusion fission. Right? It will not decay. This is nothing to do with iron being the most stable or anything like that. We are talking about decay here. We're not talking about whether or not it releases energy during fusion fission. Okay, so this is about like it on its own. If you have some element that is inside this white region, right? It sits on the table. It will sit there for 1 trillion years. It will not decay. But the elements in the gray region, in the red region, and in the yellow region, they will decay given enough time because they are unstable. Okay, they are the unstable isotopes. So what makes it stable or not stable? There is no way to tell. It's not like the previous graph where you can tell whether or not something is stable or not. Okay, essentially there's no way to predict. The only thing that you can do is this: if it's in a gray or yellow or red region, they are unstable, they will decay. That's it. If you are in a white region, you will not decay. That's it. All right. And the only small little clue that we have that tells us whether something is stable or not, right, is only at the front part. Look at this here. Okay. Notice how the white region follows the red line at first. This red line is a 1-to-1 ratio. That means one proton to one neutron. Okay. So this is like like the neutron number to proton number ratio. So N to P, right? So this red line tells us that if there's one neutron, then there is one proton in this nucleus. If there's 6 neutrons, then there's 6 protons in this nucleus. That's what this red line means. Okay, that's what this red line means. Notice how the white region follows the red line for a bit, and then the white region veers off right above the red line. So long story short, it just means this. Small elements, when they have the 1 proton to 1 neutron ratio, it means that they are stable. Small elements where there's 1 proton is to 1 neutron. Let's say the ratio of protons and neutrons, right? That means they have 1 for 1, right? They are stable. And if they are stable, they do not decay. Give me some examples of that. I'm going to zoom in here. Give me some examples of elements that are small and has the one-to-one ratio that you're familiar with from chemistry. What's that? Hydrogen is actually not really. Hydrogen is one of those anomaly ones. Come on, give me small elements. Sodium? Sodium is 2311. Sodium is 2311. Hey, your math go where? 11 protons and 12 neutrons. That's not one for one. That's not one for one. I want one for one. Yeah, you just did it. Nitrogen. Nitrogen is one of those. Right? 7 protons, 7 neutrons.
Oxygen.
Oxygen. Oxygen is what? 16.8, right? Carbon. What? Carbon 12. Right? 6 protons. So, elements, the first 20. Alright, approximately the first 20, they will be located in this white region here. Okay? But then you see their siblings. Not that stable. Yeah. Look at the sibling of carbon. Let's say okay, just an example, okay, out of like simplicity, let's not like count the dots here. This is just a rough drawing. Let's say it's 6 here, and then it's 6 there. Is that carbon 12?
Yes.
Huh? Is that carbon 12 over there? Carbon 12, right? Okay? Carbon 12. That's carbon 12. 6 protons, 6 neutrons. Hey, the graph a bit off. Like 6 protons, 6 neutrons, that's carbon 12. How about, let's say, carbon 14? Where's carbon 14, guys? Carbon 14. Tell me where carbon 14 is. Will carbon 14 be directly above? It will be, right? So I imagine carbon 14 to be there. Carbon 14. And how many neutrons does it have? 8. Try one more. How about carbon 10? Carbon 10. Where's carbon 10? This will be like carbon 10, right? Carbon 10. Right, and then it has what? 4. So the idea here is, for small elements, carbon 12, 1 proton to 1 neutron ratio, they will be very stable from decay. That means they will not decay. Carbon 12 is one of the most stablest elements in the universe, where even if you wait until the end of the universe life, okay, carbon 12 will remain as carbon 12. It will like no way that will decay at all.
So diamond.
Yeah, but it can break. And it can burn. You can also burn diamond and it becomes carbon dioxide. Yeah, if you use a blowtorch that's hot enough, you burn the diamond will psst. Right? So much for happily ever after. Okay. Right. Like this. But what if, right, what if you get like a carbon 14, for example, and you have 2 extra neutrons? So what is your understanding based on this graph, based on whatever I just said? What is carbon 14 like? Unstable. It will tend to decay. How about carbon 10? Also decay. Why? So the idea here is, if you have too many neutrons, the nucleus is unstable. If you have too few neutrons, the nucleus is also unstable. You know what I'm saying? Yeah. Okay, it's easy to understand this one. If you have too few neutrons, 6 protons and 4 neutrons, why is carbon 10 unstable? Like, why is it unstable? Nucleus. All right. Nucleus. Yeah. Carbon 10, why is it unstable? Because the protons are repelling each other. What's the purpose of having the neutrons? What does the neutrons contribute? Strong force, right? The neutrons contribute strong force to keep the nucleus stable. So in this case, carbon 10, there are just not enough neutrons to stabilize the nucleus. So a carbon 10 is unstable. In the yellow region, it will decay. Okay? Carbon 14 got extra 2 neutrons, what? Right? That's like applying too much glue. It also ends up being unstable. You understand what I'm saying? So there must be a Goldilocks region whereby it's just nice. Then it'll be stable. Okay? But as the nucleus gets bigger and bigger and bigger, as the nucleus gets bigger and bigger and bigger, what do you notice about the valley of stability? The valley of stability shows you that you need an increasing or exponential increase in the number of neutrons to stabilize the nucleus. Why? Because they are just simply getting more and more repulsions. So you need an increasing number of neutrons to stabilize the nucleus. That's why the graph, right, the white region veers off this way. Get it right? Can I? Yes.
Wait, you say strong force isn't technically in our syllabus.
Yes.
Then how do we explain carbon?
They're not gonna explain. I'm just telling you this. Yeah, they're not gonna ask you a question on this. But if I just teach you the basic A level crap, right? Then you when you go out to speak to other people, right? You speak like a kosong Singaporean, right? Then I'm not done my job. Right? If you only speak like a 6:30, right, Singaporean, I've not done my job. Like, you'll be like a half bucket of water for what? So that's why I have to go through this, right? As is noted already, even her school also doesn't have this graph in the syllabus, right? But I know that this graph appears in other schools. RI confirm have, Hwa Chong also confirm have. I know this, right? I've seen the notes before. Yeah, right. So there you go. So this graph is for decay. Okay? Okay. How about regions somewhere there? You know what? I mean, how about a carbon? How about a carbon? I don't know, carbon 8. Carbon 8. What's a carbon 8? 2 neutrons, right? 6 protons, right? Like if you were to map it out, it's like in this region. What does it mean?
It's not.
It's so unstable that it doesn't even exist in nature. Like it doesn't even register as a existing thing. All these things here, right, beyond these regions do not exist in nature. What that means is that the yellow and the gray, right, and the white and the red, right, these elements, they all exist in nature, right? It's just that the only ones that will remain stable is the one in the white region, the value of stability, while the gray and the yellow, they will decay. Okay on this? Can I? Okay. So what's up with the red region? Right, so let's work it out a bit. Let's try to understand this. In this red region, I label them as alpha emitters. That means these guys, are they stable? The red ones, are they stable? They're not stable, right? What will they do? They will decay, right? So what does it mean to be an alpha decayer? That means this element here, right? What will it do? It will, oh my gosh. It will break off a piece of its nucleus. What's an alpha particle again? 4 helium, 4 helium what? Nucleus. Okay, it's a 4 helium nucleus. All right. So these elements here in this red region are basically so heavy that the fastest way for it to stabilize itself is to just shoot out one chunk of its own nucleus. Like it will shoot off 142 helium nucleus. Okay? And this is understood as alpha decay. So at some point, some students will be like, oh, but why specifically alpha? Could it break off some other element? Like, could it break off a lithium? Could it break off a carbon? Like, can it just break one carbon off? The answer to that is no. When we have this sort of like massive nucleus trying to become stable by breaking off a part of it, it always comes out as alpha particles because that's the most energetically favorable for it to do so. But you will not need to know that in the exams, right? So I'm just telling you, right? So if some students ask me, right? So could it be any other things? No, it's just alpha. Okay, on this? Can? Okay, good. So this is your understanding of like, because they're so massive, you try to stabilize yourself by emitting, right, an alpha particle. Okay? And then these are beta minus decayers. Then the yellow regions are beta plus decayers. Okay? Did your teacher tell you that beta plus is not in syllabus? Did you even heard of beta plus before? Not really, right? Yeah, because this is not officially in syllabus, right? But I find it very hard to go and teach this thing if you don't know anything about beta plus. So I have to tell you what beta plus is, right? I have to teach you a little bit more than necessary, right? Because I don't want to give you a half past six idea of what decay is. Yeah, lah, good lah. That's good. Okay? So if you already have some introduction to decay from school, you should have learned that there are three types of decay: alpha, beta, gamma. Alpha, beta, and then gamma. Gamma is not on this graph. Yeah, gamma is not on this graph. Okay? As to why this gray region is all beta minus emitters and why this yellow region is all beta plus emitters, I'll go through that after I've gone through what does the decay do. Like, what sort of when we say decay, like what's the nuclear reaction for that? Okay? Okay? But generally, if you are an alpha emitter, it's basically you're too heavy. You need to go for liposuction. You need to cut off like one chunk of the the sides here like this, right? Cut off one here and then chuck it out, right? The fat cells here, yeah. When you're alpha emitter, you basically lose two protons and two neutrons in one shot. Two protons and two neutrons, right? You remove it in one shot. Okay, so here's the thing. Let's bring you back to the alpha emitter region. Where is it? Where? Yeah, somewhere around here, right? Okay, let's see. Okay, the red color one. Okay. Are you okay? Okay, you look at this one here. This is the alpha emitter region. All right. Let's say let's say is this guy stable or not? Huh? This one. I color him blue here. This one. Is he stable? Not stable, right? What will he do?
Lose two protons.
So the nucleus will lose two protons and two neutrons, right? So immediately he will drop down by 2 and he will move to the left by 2. This is like the chess move, right? The knight, the horse, lah. Right? When it moves by 2 by 2, right?
No, I thought it's one.
Shit. Okay, fine. I don't know, lah. But anyway, similar to that, right? It moves down by 2 and moves to the left. Because you lose 2 neutrons, you lose 2 protons, you move down and then move to the left. Wait. In doing so, what's the point? What's the point? No. What's the point? Why did the element go through the alpha decay process? To do what? To go where? To end up in the valley of stability. Not that he wants to lose mass, right? He's trying to get back to the valley of stability. Why is that? So you got to understand decay is basically the elements trying to become
Special.
stable, right? Trying to become stable. So you will lose 2 neutrons and lose 2 protons to get into this white region here.
Very special.
Okay, can right? However, sometimes one alpha decay is not enough, right? Let's say the guy is morbidly obese. Let's say he's here, right? Right, morbidly obese. Let's say he's there, okay? And then he lose 2 neutrons and 2 protons. What happens? He's still in that region. What does he do next? Another alpha decay. One more. One more.
Oh my god.
Still cannot. Oh my gosh. One more and one more. Still cannot. One more and one more. Then maybe can.
What? This guy go through so much stuff.
Yeah, this one is the hardship journey. Okay, just understand that some elements goes through multiple decays, sequence of decays before it finally becomes stable. Right? What a lot of students think right after they go through this chapter in school is that, how come the element can decay again? I thought decay already becomes stable. Right? No. Sometimes they go through multiple stages. Sometimes they accidentally go into the gray region. Then they have to decay with the gray with the way that the gray colors will decay, then trying to go back to the white region. Yeah.
What? Very top. Okay. Because if we decay, right, then it will get out of like both the gray and
Okay, this was a hand-drawn graph. Yeah. Yeah. So it's not very accurate. Okay? Yeah. I don't want, actually I should give you the actual graph. I should give you, I don't know why I went and hand draw this one. That's quite annoying also, but yeah. Anyway, my point is this. Okay. Alright. Back to the beta decays. Come, let's back to the smaller ones, right? Let's start talking about the obese ones. Right, the heavy ones. Right, let's talk about this one here. Okay, carbon 12, will it decay? No? What's right with it? So there's 1-to-1 ratio. It's a small element, so it's 1-to-1 ratio, so it can become stable, right? Okay. Carbon 14, what's wrong with it?
too many neutrons.
Too many neutrons. Carbon 10, what's wrong with it?
Too little.
Too little neutrons, or rather you can say too few protons, right? So, too many protons. Too few neutrons, too many protons. Right, sorry about that. Okay, so this and this will result in beta decay because they're not massive enough to chuck out 142 helium nucleus. So the only other decay that you can do if you're not alpha decay is beta decay. That's the only other option you have. And beta decay, there's two kinds. Beta decay has beta plus and beta minus. Okay? So there you go. Beta minus decays are too many neutrons, beta plus decays too many protons. You get what I'm saying? So how does it decay? So it decays very strangely, okay? It decays by converting one of its neutrons into a proton, or for this one, converting one of its protons into a neutron. On site, it doesn't throw it out like an alpha decay. So it's like inside here, right? Inside here, let's say one of these guys, he's like, let's say it's, okay, you see this, there are two blue ones, right? There's two blue ones, right? So what happens is that one of them will become another color. Like it will change on site. It will not get thrown out. Not like alpha decay. Because what's wrong with alpha decay? Too heavy, right? So what do? You cut it off. Right? This one here, he's got very little mass. You can't cut it off anymore, right? So the idea here is that if it has too many neutrons, then one of the neutrons here will become a proton. Right? And this one here, one of the protons will become a neutron. Okay? And it's on site. So none of the nucleus is being chucked out or anything like that. Yes. For beta decay, right? I mean, if you are not an alpha decayer, the only other way to become stable is beta decay. So it's either you have too many neutrons or too few neutrons. Yeah. Right? Too few neutrons means too many protons. And in order to become stable, your on site, your nucleons inside the nucleus, right, will actually change, become a different thing. New identity, yes, okay. Now, before we go and do the equations, right, which I'm going to do it here, okay, let's understand nuclear decay. Nuclear decay always has two words, spontaneous and random. If they ask you define nuclear decay, you have to use the word spontaneous, you have to use random. Spontaneous means what? Means that you cannot control. Okay? Spontaneous means you cannot control it. What it also means is that if you take some radioactive material and you place it on a frying pan and you go and heat it up, you go and set fire, like you go and heat it up, you use a frying pan, you raise the temperature, it will not decay faster. This is not like the chemistry rate of reaction. Okay? It will decay as and when it likes. Okay? In fact, some of these elements, some of these radioactive isotopes are bonded to a molecule. It will still decay because it's not about the electrons, it's about the nucleus. So let me give you an example. Okay? Right, carbon 14 and carbon 12. Which one is stable again? So carbon 12, what's this? Carbon dioxide. This is carbon 12 dioxide. Okay? You could also get carbon 14. You understand this? Okay. These bonds are created by what? Good, electrons. But when it comes to nuclear decay, will it affect this? No, it won't. Right? So later on, it will become something else. I will tell you what it becomes later. Right? But basically it becomes something else. But the bonds are still there. It's not going to affect the bonds. The thing will decay, but it's going to decay on site.
Oh, okay, yeah.
Remember? Okay, it's going to decay within the molecule itself. So it's not like you have to get pure carbon samples. It's not that, right? It decays on site. So isotopes have different neutrons, but they're still chemically similar to the original one. Okay, right? You learned this in chem, right? Isotopes have the same chemical reactions, right? Okay, right? This is carbon 12 dioxide. This is carbon 14 dioxide. Both of them are carbon dioxide, right? Can this be absorbed by plants for photosynthesis? Can. Okay, right? So just take note of that.
Wait, but once it becomes XO2, it cannot be absorbed. Surely.
Yeah, maybe cannot. I don't know. Yeah, I'm not a plant.
Okay.
Maybe cannot. Yeah, but later on you see what does it become. Okay, so nuclear decay has nothing to do with what molecule it's in. It will decay anyway. Right. Random. What does random mean? Random means no order, but a lot of students just stop there. Ask you to define random, you just say no order, and then you expect 1 mark. You don't get the mark, you also don't know why. Right? And you thought you got it right. Okay? You have to add on the second sentence. Every undecayed nuclei has the same constant probability of decaying in the next unit time. You want the mark, you add the statement in. Right? Otherwise, you can just throw it away, it's fine. Okay? So, random means that there's no order, but you have to add on by saying that every undecayed nuclei has the same constant probability of decaying in the next unit time. Okay, let's talk about nuclear decay reactions now. Okay, right, I'm gonna end off by attempting to finish these 3 reactions before the end of today's class. Right? Okay, so in this example, you realize that there's nothing plus this here. Right? You look at this guy. One fine day, he's sitting there, suddenly, poof, right? He becomes a different element and he emits an alpha particle. This is an alpha particle. Okay, this is an alpha particle here, like this. It's an alpha particle. You see that? Okay. So by looking at this equation, what does this tell you? Decay is no decay in general. Decay is spontaneous. You don't have to go and plus anything on this side. It will happen. Okay? Just to give you an example, let's say I have a bunch of X, right? I have a bunch of X. Like these are all X atoms, right? X elements here. These are X, these are X, these are X, like this. Okay? Right? Are they all unstable? Yeah, they are all unstable. Right? Randomly, one of them will start decaying first. And when it decays, right, the element inside is a fat element, okay? It's a fat element there, right? That's a fat element there, right? X is fat, okay? Right? And then it will just suddenly, okay, I need to become stable. Let me shoot an alpha particle out, right? And that's what happens. The alpha particle gets shot out, like this. You get it? Okay? Then what does it become? What does an X become after shooting an alpha particle off? Right? It becomes a completely different element. This is no longer X. It's a different element altogether. Why? Because it lost 2 protons. You change the proton number, you're changing its identity. Right? So it becomes something else. It becomes a V. In this example, it becomes a V. So over time, this entire pile will become, yeah, this entire pile will become a pile of V's. Right? All of them will become V's. Okay? And all the alpha particles will have been shot out everywhere already. You understand this? Okay, now alpha particle is about losing, alpha decay is about losing this alpha particle. Okay? It's not the same for beta. Beta is totally different. Okay, so let's go on to beta decay. Again, remember, if you don't do alpha decay, right? Okay, what kind of elements do alpha decay? Very heavy ones. If you don't do alpha decay, the only other decay you can do is beta decay. Okay, so beta decay. So in beta minus decay, this is your official one. This is the official syllabus one. This is the official equation that you need to know. You need to memorize. You need to be able to write it out. Okay. Let's say again we start off with X. Okay. This is just a fictitious element. I don't have. I don't want to give you any real ones. In case you think that, oh, I'm not supposed to memorize this, right? I get that all the time. Very annoying. Okay. So this is just any other random element. What's wrong with it? This is beta minus decay. Beta minus decay. All right. Beta minus decay. What was wrong with it again? Too many neutrons, right? Basically, too many neutrons. What will happen again? So the neutron inside the nucleus becomes a proton, like on site. So if let's say, for example, I have like, let me show you this. 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? 1, 2, 3, 4, 5. Okay? So yeah. So this is 5, 5, right? Let's say this is 5, 5, okay? Let's say we have like, you know, okay. So this is 7 neutrons and 5 protons, right? Do you think it will be unstable? Right? It is unstable, right? So it should be 5, 5, right? Correct or not? It should be 5, 5. What? No, as in like I mean, if it's 5 protons, you should have only 5 neutrons, right? So right now, it's a bit too unstable, right? So will it undergo alpha decay? Why not?
Because it's small.
Yeah, it's not heavy, right? It's not heavy. It's only 5 and 7 only, right? So it's not very heavy. So you can't possibly lose the alpha particle. Lose the alpha particle, half of his nucleus is gone, right? So the only way for him to decay is to either do beta minus or do beta plus. And the thing is that in our syllabus, we know there's beta minus because you got too many neutrons. What happens to the one of the neutrons? It becomes a proton. So this picture here, this thing here, okay, hang on. Later on will become something that has one less neutron, but it creates 1 proton. So one of its neutrons became a proton, like that. It didn't eject anything out of it. Okay, it didn't eject any proton or neutron out. It's not like the alpha decay. Alpha decay is literally two protons and two neutrons like this, right? It will eject out like that, right? Because it's trying to lose weight. This one cannot. This one here. This one goes like that. You understand this? Too many neutrons, one neutron becomes a proton. But in doing so, a tiny thing comes out. Right? So in doing so, a small little thing will be shot out. Okay? Right? A small little thing will be shot out from the neutron that changed into a proton. Sorry, this one becomes 6, right? Yeah, this one becomes 6 because it becomes neutrons and 6 protons. Okay, so from seven neutrons, 5 protons, it becomes 6 neutrons and 6 protons like this. Okay, but in doing so, a small little thing comes out. It's an electron. It's a tiny little electron, right? It's an electron plus an anti-neutrino. I was just trying to slip it in to see whether you, right? Okay, so this is an electron. This is an electron, and this is called an anti-neutrino. Okay, right. Okay, so the story of the neutrino is quite infamous. Your understanding is a neutrino is a small fragment of the electron. Of this electron.
Oh.
Yeah. So you see, right? Your neutron turns into a proton. It emits a electron. Correct? It shoots out an electron. It comes along with a tiny fragment of it. Can I try to remember this, huh? Okay, I'll try to remember this for now, right? There's a backstory to this. Obviously, you don't understand it yet, right? But it does come together. So there's no such thing as a beta decay that doesn't come out with an electron and a neutrino. So the thing is, this thing here is your beta minus particle. Like the beta minus particle is the electron itself. That's why it's called beta minus decay. Because the thing that's emitted is the beta particle, is the electron that got emitted. No neutron or proton was emitted. The neutron got converted into a proton in-house, right? But then the beta minus was emitted. Okay, no? Can okay, there we go. So that's it. And you got to remember that these two always comes along with each other. Okay, so this is a cursive V, and there's a bar on top. The bar indicates NT. Okay, so you have no idea what an anti-particle is. I have to reserve this for next week because anti-particles is antimatter. It's theoretical physics. It's very high level, but I'm just gonna tell you what it is and then just move on with it because technically speaking, it's not fully in syllabus. But in your syllabus, it's mentioned about the neutrino. Like in the syllabus, they mention that students are expected to know what a neutrino is, or what it does, or what it affects. So I have to ask you to remember this. One more time. Every time you have beta minus decay, the beta minus particle must always come together with the anti-neutrino, right? It comes out together, right? And we are not shooting off any neutrons or protons. The neutron is converted into a proton on site. So this is the equation that you must learn how to write from memory. So you look at this, the A remains the same, but the Z plus 1. So it becomes a different element, and the beta particle is emitted together with its anti-neutrino. Okay? Yeah. All right, now I'll save the rest for next week. Can? Yeah, I'm done here. It's 2 hours already. Okay. Next week I should be able to finish this very quickly because it's it's basically left with a half-life. Right after this is half-life. But I'm giving you another week's ahead of notice. Please go and watch the video. right? Because there's the part that I really do not want to go through, which is this, the properties of the alpha particle, beta particle, and gamma particle. I don't really want to go through all these properties, like what penetration, ionization ability, magnetic fields, electric fields, symbols. All these things are all covered in the video. They're all factual, right? Save your parents' money, watch the video. Let me go through higher level questions next week, right? And I'll go through higher level concepts next week as well, right? What was the thing that I asked you to watch? Like in the video you saw, what was the thing I asked you to watch the video for? Do you remember? Was it the last few questions?
The whole of this use like all the 11.
This part here, is it?
Which page? Which page? Yeah.
Okay, this part here onwards, is it at nuclear energy levels? Is that right?
This page.
This page onwards? That's great. I can do this next lesson, right? That means that you have to go and watch all these parts first, right? I will go through this one. I will also go through this one, right? And I'll go through energy as well, right? Of decay, right? But by next week, I'm done with nuclear already, right? Then I can go and revise other things already. Okay? The Diamond High paper. So go and do the Diamond High paper one. Okay. Those online, thank you very much. Bye bye. Any questions? Just text me, please. Thank you. Thank you, Jaya. What, Jaya? What? Sorry, paper one. I'm going. Where are you? Okay, can. I'm